Good morning, everyone. I'd like to talk to you today about some aspects of magnetism in layered nickelates. For further details, I refer you to these two papers over here. This has been a work done in collaboration mainly with Antía Botana's group in Arizona State University, but we have benefited from a long-time collaboration with Warren Pickett's group at UC Davis, John Mitchell and Mike Norman and their group at Argonne National Lab, and also Dan Dessel from the University of Colorado in Boulder. I will present a few ab initio calculations carried out mainly using density functional theory with standard codes like Bing2K or VASP. For the experts in the audience, I have used GGA for structural relaxations, and we have used the LDA plus U method with two different flavors for treating correlations. I will try to address two main questions here in this talk. The first one is whether there is an antiferromagnetic insulating phase at any point of the nickelate phase diagram, and also if the nickel 2+ dopants are magnetic or non-magnetic. First, I will start recalling the basics of the electron structure of bulk neodymium nickelate. If you look at the band structure here, this has been plotted for a square root 2 times square root 2 in plane supercell. That's why we have two nickel atoms in the band structure. They are coupled antiferromagnetically. And we highlight here the nickel DC squared bands. We see that there's particularly this largely dispersive band that crosses the Fermi level and makes the system metallic. This band is formed by a hybridization of the nickel DC squared bands with rare earth D bands. So even though this system nominally is a nickel plus D9 compound, it is self-doped so that the X squared minus Y squared band is not completely half full. So the resemblance with the cuprate phase diagram, where this point here at D9 filling is an antiferromagnetic insulator, does not seem to appear for neodymium nickel O2 for these nickelates because this is metallic. So we can start thinking about playing with this system, and we can do computational experiments with this. The first thing we did is calculating a monolayer like this of neodymium nickel O2, and substantial changes occur to the electron structure. Again, if we look at the band structure, looking at the nickel DC squared bands, we see here that they are largely localized and completely full. So the system is indeed an insulator. It is gapped, and the ground state is formed by an antiferromagnetic coupling with this checkerboard in plane ordering. So the antiferromagnetic insulating phase appears for this monolayer neodymium nickel O2. If we try to do another computational experiment by using this multi-layer system alternating neodymium sodium O2 and neodymium nickel O2 along the z-axis, we see that this system retains the neodymium off-plane coupling, but the nickel-nickel off-plane coupling is largely blocked by this sodium O2 layer here. If we look at the band structure, again, seeing the nickel DC squared bands, they are completely occupied below the Fermi level, and the system is gapped, and it's again an antiferromagnetic insulator. So where can we find in nature something that looks like these computational experiments that we've seen? If we look at the reduced Rutherford Popper series for different n values, n 3, 4, 5, 6, we see that structurally they are formed by n nickel O2 planes, which are isolated along the z-axis by this fluoride slab here, this blocking layer fluoride with fluoride structure. This makes that these nickel O2 planes are somewhat localized in space. Some of these systems have been studied already. The n=3 member with praseodymium as rare earth is a metal, and the n=5 member with neodymium as the rare earth has been found to be a superconductor. So if we do virtual crystal approximation calculations with this reduced Rutherford Popper system, so that all of them are nominally at nickel plus D9 filling, this is done by shifting the position of the chemical potential, all of them are antiferromagnetic insulators. We can see here the band structures, they all look very similar, they are gapped, and we see the nickel DC squared bands completely occupied, and the main coupling in the plane is, as always, antiferromagnetic. So this reduced Rutherford Popper series have in them a point in their phase diagram that is an antiferromagnetic insulator, which is at D9 filling, just like the cuprates. We already studied something similar to this 5 years ago with doping praseodymium-438 with cerium. What we saw is that introducing cerium in this system, cerium would be cerium 4+, it would dope the system with electrons, moving it in the phase diagram in this direction, and the nominal nickel plus D9 had this band structure, which is again gapped and antiferromagnetic in the plane, which is very similar to the VCA calculations I just showed you. What we saw at that time is that, well, okay, if you dope praseodymium-438 with some cerium, eventually you could end up exploring the superconducting dome region at the appropriate filling. The second question we wanted to address in this talk is what happens when you strontium dope neodymium nickel O2. When you dope it with strontium, you introduce holes in the system, and these holes go in the nickel d bands, which are the states that are closer to the Fermi level in these nickelates. And these nickel 2+ dopants that appear, they can be either low spin or high spin, depending on the strength of the crystal field splitting versus the Hund's rule coupling. In the square planar environment, one expects that the crystal field splitting would be large, and maybe this solution is found. And in this case, nickel 2+ dopants will be non-magnetic, similar to what happens in the cuprates. In the cuprates, the dopants are non-magnetic because they form these sunrise singlets due to the involvement of the oxygen p bands. In this case, the oxygen p bands are farther away, and we have to play with the nickel d bands instead. So we did supercell calculations for different dopings with a 3x3 or 2x2 supercells. I will discuss a bit later this 4x4 type of supercell. And for these and these different strontium doping levels, we calculated the total energy differences between the high spin and low spin configurations. What we saw is that using this flavor of the LDA plus U method, the AMF, always the system prefers to be low spin for either lanthanum or neodymium, nickel O2, and only at large U values, and for this particular flavor of the LDA plus U, the so-called fully localized limit, the system prefers to be in a high spin state. Our past experience with other nickelates has shown us that the AMF provides a better agreement with experiments in this system. So our conclusion from the calculations is that always the low spin state will be favored, and nickel 2+ dopants will be low spin. We can explore this in a bit more detail in this 4x4 supercell. What we did is a 4x4 supercell, but with all 4 strontium dopants surrounding in a clustered way this nickel cation, which becomes nominally nickel 2+. Probably this is not the ground state situation for the strontium dopants, but it allows us to study a nominally nickel 2+ dopant locally. And we can study it in a high spin state or in a low spin state. Always the low spin state situation is more stable. And we can see here with these partial densities of states that the electronic structure that it produces in a low spin state is completely different to one in a high spin state. In the low spin, more stable solution, we see that the nickel DC² bands are completely full and away from the Fermi level. Whereas in the high spin situation, they would be occupying, populating the Fermi level. In the low spin solution, which as I say is a more stable one, the nickel D bands that are closer to the Fermi level are the X² minus Y² bands, just like in the cuprates. And this would be different in this magnetic solution that, as I say, is not stable. We can see that as you dope, the electronic structure changes. For example, the oxygen p bands move closer to the Fermi level, so the charge transfer energy that is larger in the nickelates than in the cuprates gets reduced. The system becomes more cuprate-like in that respect. And also the rare earth D bands move further away from the Fermi level as you dope. And this reduces the self-doping effect that we discussed before, that in neodymium nickel O2 or in lanthanum nickel O2, it produces this departure from the cuprate-like electronic structure. So as you dope lanthanum nickel O2 or neodymium nickel O2, the electronic structure recalls more that of the cuprates. That's one of the main messages of my talk, is that mimicking the electronic structure of the cuprates brings you closer to finding superconductivity, as has been seen by experiments. The other two messages is that we can recover parts of the phase diagram of the cuprates. For example, the antiferromagnetic insulating phase can be recovered, even though you don't find it in the infinite layer system because of dimensionality effect and off-plane couplings. If you block this, for example, by using reduced rather than Popper systems, you can recover the antiferromagnetic insulating spot in the phase diagram typical of the cuprates. And another message is that we know of two ways to reach the superconducting dome in these nickelates. One of them is doping with strontium, the rare earth nickel O2. We have seen from our calculations that in that case non-magnetic dopants appear. We know that the N=5 member of the reduced rather than Popper series is a superconductor, but we propose that doping the N=3 member, the praseodymium-438 with cerium, would eventually lead you to explore that part of the phase diagram. Those are my main messages, and I thank you for your attention.